This video is about the astable, an oscillating circuit. Basically a very simple circuit, but well, oscillators are beasts if you think about simulation. They don't have a stable operating point because, well, they oscillate, especially for starting a transient simulation. So sometimes they oscillate only with difficulty in the simulator, but sometimes even they refuse to oscillate. Of course, you can do something about that, and that's what this video is about. Okay, here is a template. I've put down some capacitors, resistors, voltage sources, power supply, and what is missing is the bipolar devices I want to add. Okay, so let's start with some basic NPN transistors, the generic transistors delivered with KiCad ngspice. Add symbols, choose NPN, and have a look at the simulation spice library where there is the NPN transistor, and we choose exactly that. You put it here, another left mouse click for the second device. Okay, you just have to turn it around, right mouse click, transform selection, mirror, and put it in here. Yeah, so this circuit seems to be ready. How it's working? Well, imagine that this node here, the collector node of Q2, is suddenly going down to 0. This pulse will be transported over the capacitor onto this line. This line has been at 0.7 volt base emitter voltage of this transistor. Now goes down by 9 volt. So down to -8. And now it is charging via this resistor. This capacitor will be charged. This one is about 0. This will be charged from the -8 volt up to 0.7. And at 0.7, this one starts conducting. And we have the voltage of the output going down. And then this pulse is transported via this capacitor over to this baseline, this which goes down, and which will be charged with this capacitor, and then the next cycle is starting. Yeah, so what do we want to do? We want to do a transient simulation. We should have a look at inspect simulator, the transient which is here, already set this tab. I have a look at it, and we have a time step of 1 micron and the final time of about 20 milliseconds. And if I divide 20 milliseconds by 1 micron, I'm expecting around 20,000 time steps. So 20,000 times calculating the next value. Okay, let's just try to do that. Starting here. And I see, oh, this thing is indeed oscillating, but a little bit strange. Not a very smooth ride. It oscillates sometimes faster and then slower again. And what you see here, the number of data rows is about 200,000. So not 20,000, but 200,000. Something has happened inside of the simulator which leads to this critical result. Even if it looks nice, a factor of 10 simulation time increase, that's not what we want. Yeah, what could it be? It could be that it is about the model parameters of these devices here. So let's have a look. Double click onto the symbol, going into the simulation model, and here we can have a look at the parameters. And if I look at capacitance parameters, which is important for dynamic simulation like an oscillator, I see there is no value and everything is 0. This is perhaps not good. So let's give it here, let's say 10 picofarad. And this is the junction emitter capacitance, the junction collector capacitance. Oh, let's give it 5 picos. Okay, well, of course, I have looked it up before. Another parameter which is of interest, which we should change from its basic 0, is the base resistance. Because the capacitances we have just added are charged via the base current, the base resistances. So let's give it 100 ohms here. Okay, and okay. So I've changed the parameters of this device. I could do the same with this device, but what I'm doing now is just delete it and duplicate this. Because duplicating also means duplicating of any parameters or models changed. I have the transformer selection to mirror it, put it in here. Yeah, so this looks okay. So let's again start a simulation. I'm doing the simulation here, and of course it's much faster, which is very nice. And if you look at the number of data rows, now we are near we have 21,000, so it's close to the anticipated values, a factor of 10 less, and so the simulation time is a factor of 10 faster. But something is a little strange when I look in detail into our output graphs here. Let's have a look. Let's enlarge it. There seems to be some oscillation. And in fact, it is from time step to time step. Every 1 micron, another micron, we have this ringing. And in fact, it's an artificial oscillation. It's an artificial oscillation, so-called trap ringing. And we want to get rid of that. Can we do that? Yes, we can. Let's open a text box and put into this text box dot options with the integration method changed from trap to gear. So we don't have a modified trap filtering like other simulators do. We just change the integration method. Put it in here. Go again down to our simulator window. Rerun the simulation. And here we are. This looks really nice. Okay. Yeah, so the question is, why mingle around with these internal transistors? Could we improve ngspice? Yes, we can. But of course, it's a discussion with historians. These default values are there for 40 years. Should we change them? I would like to do that, but let's see. So maybe better we use commercial transistors. Yes, and so let's do this. We go here, remove our standard NPNs, and looking for something different. We add symbols, and I would like to look for the BC848 transistor. Okay, so yeah, let's put it in here. So yes, when we add a commercial transistor or a foreign transistor, we need a model for this transistor. Yeah, so let's have a look for the model for this transistor. And indeed, well, you do an internet search. We, for example, look at Nexperia website, searching for BC848B. Okay, here we are, and we have a look at the documentation. When we go down, we see that there is a SPICE model available. Click on that, and here it is, the SPICE model. So we mark it copy it, put it in a text editor or directly into the, as a text file directly into the project directory. Well, I have done this already. So I could go on here, adding the model to the transistor. Double click onto the symbol, choose simulation model. We want to load the model from a file. Let's have a look where to find this file. It is bc848b.txt. And the model name is bc848b. And here we are. Not yet. We have to look at the pin assignment, because if you see a bipolar transistor and you see that the collector node has the pin number 3, then you have to be alerted, because in standard SPICE the collector is the first node, it's number 1. So we have to do some pin assignment here. Okay, yeah, where do we get this pin assignment from? I think I clicked OK first and then go back again to the simulation model pin assignment, because then the model is loaded here and I can have a look directly. Well, Xperia is tricking the users a little bit. Yeah? They talk about the package pin. Base is number 1. Yeah, it is. Emitter is number 2. Collector is number 3, like you find it here. But this is not the SPICE model pinning. They write it, but they don't tell us what is the SPICE model pinning. Yeah, we have the subcircuit here with nodes 1, 2, and 3. And indeed, these is collector, base, emitter. They don't tell us. But you see, if this is the main transistor directly connected to the input, and it has collector, base, emitter, because this is a SPICE transistor, then we know that is collector 1, base 2, emitter 3. Okay, so what is collector? Collector is to become 1. Emitter is to become 3. And base is to become 2. And hopefully that's it. Okay. Okay. Now we can duplicate this device, including our model and pin assignment. Transform the selection, turn it around, mirror it horizontally, put it in here. And okay, let's try what our simulator is saying. We have the simulator window or still open, and we do our transient simulation. What do we see? Bah, it doesn't oscillate. It refuses to oscillate. Yes, and this happens or can happen because the astable oscillator may find a stable operating point, a stable DC operating point. Just think about having this, now the base of the transistor 1, 2 and the base of a transistor 1, both at 0.7 volt. Both collectors are low. No switching is happening, no pulse is transporting, nothing is happening. Well, then it just stays there. Yeah, what can we do? We have to do something about this. We have to introduce some asymmetry. And the asymmetry could be that we put this base node B1 here to 0. And we do this by adding another command. We can do it into the same text box. So double click here. And then we write down .ic, initial condition of the node voltage of /B1. Remember, the slash has to be added when we have local labels here. And this should become 0. So, okay, we have added this. And now let's try again. Inspect your simulator, or choosing the simulator window, which is just there. And we rerun a simulation. And here we are. Simulation is fast. We have about 21,000 data points. And the curves looks nice because we have still enabled the gear method for this oscillator. Thank you.